These days, if you follow the news for even a few minutes, you keep hearing the same word, uranium. Countries are enriching it, governments are watching it, and the world treats it like one of the most dangerous materials on Earth. But what exactly is uranium? Why does one element keep showing up in conversations about energy, war, and weapons powerful enough to erase entire cities? And how can something no bigger than your fingertip hold as much usable energy as a ton of coal? Today, we're breaking down why uranium may be the most powerful element on Earth. And to understand how humanity got here, we have to go back to 1789, when a German chemist named Martin Heinrich Klaproth was studying a strange heavy black rock called pitchblende, and stumbled into a discovery that would change history forever. After isolating the new substance, Klaproth named it uranium, inspired by the recently discovered planet Uranus. For the next 100 years, uranium remained little more than a scientific curiosity. It was used to color glass and ceramics, giving them a yellow-green glow that looked beautiful and, at the time, harmless. No one realized that behind that color was a force that would eventually reshape the modern world. That changed in 1896, thanks to an accident. Physicist Henri Becquerel left uranium salts near a wrapped photographic plate and later found that the plate had been exposed, even though no light should have reached it. Something invisible from the uranium had passed through the covering and left its mark. That unexpected result led to one of the most important discoveries in modern science, radioactivity. And from that moment on, uranium was no longer just an unusual material. It had become a doorway into a completely new kind of power. Becquerel's accident gave scientists an important clue, but Marie and Pierre Curie took the story much further. They began to understand that uranium was not just a heavy metal sitting there quietly. It was constantly giving off energy from deep inside the atom itself. That raised a bigger question. Why does uranium behave this way? Part of the answer lies in the fact that uranium comes in different forms, known as isotopes. The two most important are uranium-238 and uranium-235. Uranium-238 makes up almost all natural uranium on Earth. It is the heavier, far more common form, but it does not split easily in the way needed for most nuclear reactions. U-235 is different. It makes up less than 1% of natural uranium, but it is the isotope that changed history. Unlike U-238, it can be split under the right conditions, releasing an extraordinary amount of energy. That one property is what turned uranium from an obscure heavy metal into one of the most consequential materials humanity has ever discovered. And even that is only part of the story. Uranium is older than Earth itself. It was forged in some of the most violent events in the universe, likely during supernova explosions or the collision of neutron stars. In other words, uranium is not just a material from the ground. It is leftover cosmic matter from a much older universe. That is what makes it feel almost unreal. Tiny amounts of uranium already exist in the soil, in water, in the food we eat, and even in the human body. It has been part of Earth's natural environment for as long as the planet has existed. And long before humans built nuclear reactors, nature had already done it. About 2 billion years ago, in what is now Oklo in Gabon, uranium deposits and groundwater combined under the right conditions to create a natural fission reactor. It ran on and off for hundreds of thousands of years, all without engineers, machines, or control rooms. So uranium is not just a fuel, and not just a weapon material. It is a natural substance with a story that begins in the stars, runs through the earth beneath our feet, and ends in one of the most powerful technologies humanity has ever learned to control. So, Mother Nature was way ahead of us by about 2 billion years. But humans were not about to be left behind. We figured out how to trigger what we now call nuclear fission. Think of uranium-235 as the first domino. When a neutron bumps into it, the nucleus becomes unstable and splits apart. But here's what makes that so important. When it splits, it does not just release energy. It also sends out more neutrons, which can strike other uranium-235 atoms nearby. Just like that, in a fraction of a second, a chain reaction begins. releasing a tremendous amount of energy. That is the secret behind uranium's power. But there's a catch. Uranium, in its natural form, is still far from reactor ready. The process starts in mines in places like Kazakhstan or Canada. The ore is crushed and processed into a concentrated yellow powder called yellow cake, but it still cannot fuel a reactor yet. Why? Because most of it is still uranium-238, while the amount of uranium-235 remains very small. To fix that, uranium has to go through one of the most difficult engineering processes on Earth: uranium enrichment. You've heard those words 1,000 times before. That is exactly what Iran has been trying to do, and a major reason it has paid such a heavy price. To raise that tiny share of uranium-235, engineers use giant centrifuges that spin at extraordinary speeds, separating a small fraction of uranium-235 from the far more abundant uranium-238. Want to light up a city? You only need about 3% to 5% uranium-235. But to build a weapon, you need a massive jump, over 90%. But the story does not end there. Right now, most nuclear plants use only that small fraction of uranium-235, while most of the uranium-238 is left unused. But scientists have found another path: the breeder reactor. This type of reactor can convert uranium-238 into plutonium-239, a new fuel that can also be used to produce nuclear energy. That means the same uranium ore could yield far more energy than it does today. If that technology is developed safely and successfully, uranium could become a much more long-lasting energy source than it appears today. Still, that is not what made uranium infamous. Its darkest impact came through war. When scientists realized what highly enriched uranium could do, uranium crossed a line in human history. Inside a reactor, fission is controlled. Inside a bomb, it happens almost all at once. The result is a devastating release of energy in a fraction of a second, powerful enough to produce a blast, heat, and radiation far beyond anything conventional explosives can deliver. In 1945, the world saw that reality in Hiroshima. From that point on, uranium was no longer just a scientific discovery. It had become the heart of a weapon, capable of changing war, diplomacy, and the balance of power itself. After World War II, the world tried to stop that power from spreading without limit. Under the Nuclear Non-Proliferation Treaty, a small number of states were recognized as nuclear weapon states, while most other countries agreed not to develop them. The reason was simple. The wider nuclear weapons spread, the greater the risk of destruction on a scale civilization may not recover from. But history did not stop there. Once the science was known, uranium became more than fuel. It became deterrence, leverage, and survival. That is why some countries still try to move closer to nuclear capability today, not always to launch a weapon, but to change how rivals deal with them. In geopolitics, that kind of capability can act as a shield, a threat, or a bargaining chip long before a weapon is ever used. But uranium is not just about weapons. Consider modern nuclear submarines. With a relatively small amount of fuel, a massive vessel can operate for years without refueling. That is one of the clearest examples of how much energy uranium can hold. For all its reputation, natural uranium is only weakly radioactive. Under ordinary conditions, brief contact with solid uranium is not usually the main danger. The greater risk comes from uranium dust getting into the body, where its chemical toxicity can damage organs such as the kidneys. The large-scale radiation disasters people think of, like reactor accidents, usually come later in the story. Natural uranium by itself is not concentrated enough to produce that kind of runaway event. The real danger appears after uranium is enriched and used as reactor fuel because fission creates highly radioactive byproducts. If a reactor loses control through technical failure, human error, or disaster, those are the materials that can escape into the environment, contaminating air, water, and soil, and sometimes forcing entire communities to evacuate for years. And there is another remarkable side to the story. Part of the heat still trapped inside Earth comes from the slow radioactive decay of elements like uranium deep underground. That internal heat has helped keep our planet geologically active over immense spans of time. Without it, Earth would likely be a very different world. Ultimately, uranium feels a lot like the fire of Prometheus. It can power cities, push civilization forward, and perhaps one day take us farther into space. But in the wrong hands, or under the wrong decisions, the damage can last for generations. That is what makes uranium more than just another element on the periodic table. It is a measure of human responsibility. The same material that can help build the future can also destroy it. And maybe that is the real story of uranium, not just how much power it holds, but whether we are wise enough to live with it. If this changed the way you think about uranium, let me know in the comments. Do you see it as humanity's greatest energy source, or its most dangerous invention? And if you enjoy deep dives like this, subscribe for more stories hiding inside the science of everyday life.